Today we'll learn about UV visible spectroscopy of transition metal complexes. One of the most interesting aspects of transition metal complexes is that they often have a color. So they're fun to look at, and today we'll see what we can learn by looking at the colors or the spectra of transition metal complexes. First of all, what is a spectrum? A spectrum is a plot of absorbance versus wavelength when we analyze the absorption spectrum of the complex. You might remember that 400 nanometers corresponds to visible wavelength and high energy, or make that 400 nanometers and purple wavelengths. That corresponds to high energy, and 700 nanometers is red color, which is low energy. So in a UV visible spectrum, what we find then is differential absorbance. The peak of the absorbance, right about there, corresponds to the maximum absorbance. And if we had an instrument that was recording the spectrum, we could easily read down and find out the exact wavelength of the maximum absorbance. What causes absorbance? It's due to the differential absorbance of light. Assume for simplicity that we've got a D1 octahedral transition metal complex. The single electron is in a T2G orbital, and that electron can be promoted if the appropriate energy of light is supplied by a photon. So then the electron goes from the ground state to the excited state, and eventually it will relax back down to the ground state so the cycle can repeat itself. The excited state only lasts for a split second, and then the electron returns. But effectively then, the transition metal complex acts as a filter for the entire range of colors of the visible light. It will absorb some colors and transmit others. That relationship causes the color. So for example, the artist wheel helps us look at the relationship between color absorbed and color transmitted. So imagine a circle that is divided into 6 parts. Starting with red, which would be the longest wavelength and lowest energy, we can go from red to orange to yellow, in this case counterclockwise, on through green, blue, and violet. So if a complex, for example, absorbed only violet light, it would appear to be the sum of all of the remaining colors, and the artist's wheel help us learn that that sum of colors would correspond to a yellow color. So that's the color that's directly across the artist's wheel from a wavelength that is absorbed. So let's just work through a quick example. Imagine that we have 2 copper-2 complexes. One of them is in the leftmost container and is blue. The other one is in the rightmost container and is green. So which one has the larger delta? Let's see how we can figure that out, not even using the spectra themselves, but just using the colors and the color wheel. So the way that that would be done would be to look at the color wheel and quickly deduce that the solution that appears to be green is actually absorbing red. Similarly, the blue solution is absorbing orange. We know that orange light has more energy than red, therefore the complex that appears blue has the larger delta. We can take this one step further in this case because we know that both complexes are copper-2 plus. Therefore, we could say that the complex with the blue color has the larger or the stronger field ligands in this case because they are producing the larger splitting. We have to be a little bit careful with this analysis, which is a bit simple but useful for a couple of reasons. The first is that this analysis assumes that the transition metal complex only has one peak in the visible region of the spectrum. And for reasons that we won't go into here, many complexes have two or even more absorbances in the visible region. So in order for this analysis to be effective, we want to make sure that we're comparing complexes that are related in some way so that we can be sure that we're comparing apples to apples. The other thing that can happen is that one complex might absorb in the UV region of the spectrum. If that's the case, all of the visible light is transmitted and the sum of that is colorless. So a large field splitting will appear to be give rise to a colorless complex. But again, bottom line takeaway, that the color of a complex is related to the d orbital splitting, and the color is caused by promotion of an electron from a ground state to an excited state.